Let's continue with the test review. Let's start on chapter 18 topics. So the first bullet here, movement and energy of charges in electric field. So it's talking about how you need to know what happens to a charge as it moves in some external field. And the best way to represent that is to draw these two plates, a positive plate and a negative plate, because you know that there's going to be an electric field between the two, and it just helps you visualize things. So the first thing that you need to know is that the electric field points towards a decreasing potential, right? So if this is a positive plate, it's going to produce a higher potential, and I just made up a number, 100 volts. It's going to produce a higher potential than a negative plate. So I just made up a number and said that the negative plate was at a potential at 0 volts, just to make life simpler. And so the electric field points towards a decreasing potential, right? It points towards a lower number. It points from the positive plate to the negative plate. So that's just to help you visualize, because you're going to want to draw this picture when you have this problem on the test. So then you need to know, okay, well, if you were to put a positive charge inside this field, then what would happen to it? So if you put a positive charge here, and I'll just redraw this again because you're going to want to draw this as well. So if you put a positive charge here, well, by definition of the electric field, it's going to experience a force in the same direction as the field. So you know it's going to experience a force this way. So it's going to move from a high potential to a low potential. You see that it moved from the 100 volt region to the 0 volt region. So that's what this one is saying. You can also think of it as it's moving away from the positive charges and towards the negative charges because it's attracted to the negative. And then it's going to gain kinetic energy and lose potential energy. It's going to speed up. If it experiences a force, it means it's going to accelerate this way. It's going to speed up and gain kinetic energy, if you remember, is 1/2 mv squared. And in gaining that energy, because of conservation of energy, it must lose potential energy. So if we go and look at our equations here, that will help us with this. So we have here, first of all, that this is talking about there's a potential difference between 2 points. So the potential difference between these two would be 100 volts. Now technically, if you're going from left to right, you're going to a lower potential, so the potential difference would be negative 100 volts. And then what the equation sheet is saying is that this potential difference is equal to the field that's in between those 2 points. And let me just minimize this a little bit here. Alright, so it's equal to the field between these 2 points times the distance, so there's a distance d between these 2 points as well. So when you are trying to use this equation, that's what you want to picture. The potential difference is related to how strong the field is. So the more potential difference between these two, the stronger the field between those 2 plates. And then the second part of the equation here, which says delta V, right, you want to look at it separately, just ignore the middle part, delta V equals delta UE per Q prime. Q prime is this test charge, it's this one right here that's moving here. So it's saying, okay, as a test charge is moving through a potential difference, so in this case from this plate to this plate, there's a potential difference there, then its potential energy will change. So if you want to find out by how much the potential energy changes, then you would do Q prime times delta V by just rearranging this equation here. So if this is a proton, then you know the charge of that proton is E, right? This number right here, that's the charge of your proton. You'd multiply that by the negative 100 volts potential difference, and that would show you a negative change in energy, which would go along with what it said here, that it was going to lose potential energy. So I'm just trying to make sure that you see how the equations relate to these conceptual ideas. Now, these bullets here are talking about what happens under the influence of an electric field. But it is possible somehow that you're told, hey, this charge here is actually moving in the other direction. It doesn't tell you why, but it means that something must have forced it to go that way initially. So in that case, then these would be reversed, right? It would go from a low potential to a high potential, and it would gain potential energy, but it would lose kinetic, right? It doesn't want to go that way. It's going to slow down as it approaches that way. It's going to lose kinetic. So that is an option as well, but then it would tell you that, hey, it's actually going this way towards, maybe it says towards the higher potential. So that tells you, okay, it's not just under the influence of the electric field. So make sure that you only apply these bullets if it's under the influence of the electric field. And then you can do the same thing with the negative charges. You could draw the picture, and if you draw the picture for the negative charge, well, if it were just under the influence of the electric field, you know that that negative charge would want to go that way. So that's why it's moving from the low potential, right, this is 0 volts, to the high potential. But just like the positive charge, it's going to experience a force, which means it's going to accelerate. And so it's going to speed up, and it's still going to gain kinetic energy and lose the potential energy. Which way is the force on this one? Well, the electric field is still this way. Oops. The electric field is still this way, right? It's always towards the lower potential. But a negative charge experiences a force in the opposite direction as the field. So it would experience a force to the left. But this would still apply. And the last thing here is, okay, what about if there's a question asking about the work, right? So how much work is done on this negative charge as it moves from this low potential to this high potential? How much work was done? So if you look at the equation sheet, it's the electric field that's moving the charge. So this gives you the equation right here, that the work done by the electric field is negative Q prime delta V. So if we just apply that to here, well, the charge on the electron is negative E. So you put a negative and then a negative E for the charge, right? This is Q prime. And then the potential difference, it went from a low potential to a high potential. So it's a positive number. So whatever that positive number is, in this case, maybe 100 volts, right? So that means that the work done by the electric field would be a positive E times 100 volts. That's also known as 100 eV. And you could convert that to joules. We talked about how EV is a unit of energy, and there's a conversion factor here. 1.6 times 10 to the negative 19 joules for 1 EV. So you could multiply by that conversion factor to get the work in joules. But the work would indeed be positive because the force is to the left and the displacement is to the left, and that results in positive work. And then the last thing here is, what is the work done by an external force? Well, if the work done by electric field is positive, then the work done by the external force would be negative. So what we're saying is, if we had an external force here, then in order to prevent this charge from just crashing into this plate here, the external force would have to be applied this way to restrain the charge as it's moving to the left. So it would just be the negative of this number. And in terms of energy, this means that the work done by the external force would increase the potential energy, while the work done by the electric field here decreases the potential energy.